All the work we have done so far was devoted to developing a systematic method of solving systems of linear equations. Since this task is now behind us, I would like to spend some time to talk about a few examples of practical applications that will involve such systems of equations. And so, in this segment, I will talk about the problem of computing traffic flow in a network of streets. Then we will move on to the problem of calculating currents in electrical networks. And then I will explain how systems of linear equations can be used to balance chemical reactions. Let's move on then to the first topic. Here we have a diagram that shows a small network of streets. And for simplicity, I will assume that all these streets are one-way streets and that the direction of traffic on each of them is indicated by these arrows. For reference, it will be also useful to name intersections in this network, so I will call them A, B, C, and D. Now, one of the basic problems that traffic engineers face is to find the flow rate of cars on each segment of streets. Such data is needed to determine how traffic lights and traffic signs should be set up, how fast the road surface will be wearing off, and so on. Naturally, the most direct way of finding information about the flow of traffic is to simply go on a street and count the cars. Let's assume then that we placed vehicle counters on a few streets and that they recorded the following data. On average, there are 85 cars per hour traveling on the street leading to the intersection A. There are 70 cars per hour on the street joining intersections C and D, 45 cars per hour on the street joining intersections D and B, and that there are 120 cars per hour on the street exiting from the intersection B. Now, we could, of course, determine in the same way, by counting, the flow of traffic on all the other streets. But in practice, especially when we are dealing with large networks of streets, this would be costly and time-consuming, since we would need to get a lot of measuring equipment, and then we would need a lot of people who would install and supervise that equipment. So it would be much more efficient if, based on this partial data that we have, we could somehow compute the flow rate of traffic on all the other streets. And we'll try to do just that. We will denote the traffic flow on the streets where we didn't take measurements by variables x1, x2, x3, x4, and x5, and we will try to see if we can compute the values of these variables using the data that we have at hand. Now, our computations will be based on a couple of basic observations concerning traffic flow. The first observation is that the flow of traffic into any intersection is the same as the flow out of that intersection. This is, of course, what usually happens. If, say, 100 cars enter some intersection during 1 hour, then the same number of cars will exit that intersection during that hour. It may happen occasionally that, say, a car crashes in the middle of the intersection and never leaves it on its own, but these are rare instances, and usually what gets in gets out. The second observation is similar. The total flow into the network of streets from the outside of the network is equal to the total flow out of the network. Now, we will use these two observations to set up some equations And these equations will be of this general form: whatever goes in must be equal to whatever gets out. Let's apply this first to the total flow of traffic in and out of the network. And in our network we have two streets leading into the network. The street leading to the intersection A brings 85 cars per hour, and the street leading to the intersection C brings x4 cars per hour. And this means that altogether we have 85 plus x4 cars per hour entering the network. On the other hand, we also have two streets via which traffic leaves the network. The street leaving from the intersection B carries 120 cars per hour, and the street leaving from the intersection D carries x5 cars per hour. So altogether there are 120 plus x5 cars per hour leaving the network. Next, we need to have a look at what happens at each intersection. And so, at intersection A, we have only one street that brings cars in, and this street carries 85 cars per hour, and this must be equal to the flow out of this intersection. We have two streets going out with flows x1 and x2, and so the total flow out of this intersection is x1 plus x2. At intersection B, we have three streets that bring traffic in, and the total flow in is x1 plus x3 plus 45, and then there is one street going out, and this street carries 120 cars per hour. Next, at intersection C, there are two streets going in, and these streets bring x2 plus x4 cars per hour, and there are also two streets going out, and these streets carry 70 plus x3 cars per hour. And lastly, at intersection D, the flow in goes along a single street that carries 70 cars per hour, and there are two streets going out, and these streets carry 45 plus x5 cars per hour. And so these are all equations that we get here. As you see, we obtained then a system of equations in 5 variables, and what we need to do next is to find solutions of this system. As the first step, we will rewrite this system so that all variables are on one side of these equations and constants are on the other side. And once we do it, the system will look like this. Next, since this is a system of linear equations, we can follow our usual procedure to find its solutions. And so, as the first step, we write the augmented matrix of the system, which will look like this. By the way, one thing that you can notice about this matrix is that most of its entries are zeros. A matrix like this, consisting mainly of zeros, is called a sparse matrix. Such sparse matrices appear very frequently in many practical applications. In any case, in order to solve our system, we need to perform row reduction of this matrix, and, as you can check, as the result of row reduction we obtain this matrix in reduced echelon form. In order to read the solutions of the system out of this reduced matrix, let me label its columns with the corresponding variables. And now, as you can see, in this reduced matrix, we don't have a leading one in the column of constants, so our system is consistent. And we also have no leading one in the column of x3, So x3 is a free variable. The solutions of the system are then as follows. From the first row of the matrix, we get that x1 is equal to 75 minus x3. The second row gives that x2 is equal to 10 plus x3. Then, as we already know, x3 is a free variable. Then, from the third row of the matrix, we get that x4 is equal to 60. And finally, from the fourth row, we obtain that x5 is equal to 25. And so, these are the solutions of our system. Now, let's get back with these solutions to our network of streets. If we enter these solutions into this network, we will get the following picture. As you see, as the result of our computations, we got here some concrete numbers. We obtained that there are 60 cars per hour entering the intersection C from the outside, and that there are 25 cars per hour leaving the network through the intersection D. As you can also see, we did not determine completely traffic flow on all the streets, since there is still one variable, x3, the value of which is undetermined. What this means is that we have started our computations with insufficient data. These red numbers that came from physical measurements of traffic flow are simply not enough to determine traffic flow completely. What we see, though, is that we need to go and measure traffic flow on just one more street, this one, joining intersections C and B, and then after the single more measurement, we will know the value of x3, and then we will know the flow of traffic on every street in the network.